Reliability means it not only has to do what it's supposed to do occasionally, it has to do what it's supposed to do always. Well, always. It depends on the kind of program, really. If we're back in the operating room, it has to do it always. You know, how many patients are we willing to have die before we decide the software is no good? It has to do it always. If it's a game program, maybe we're going to be happy enough if it does it 90% of the time. You know. I don't have anything against games. Don't think I do. The economics are different. You're going to spend more for a hospital operating room system than you are for a game. That's just all there is to it. You're going to be willing to spend more. You know. Robustness is not exactly the same thing. Not exactly the same thing as reliability. Reliability says that it should always do the right thing. Robustness says that it shouldn't explode under weird circumstances. It should do something reasonable. If it gets into a state that it doesn't know what's going on, you know, you're logging in and you know, you're giving your personal information and you enter your age as being -1 year, the computer shouldn't crash just because it sees an age of -1. It should behave responsibly. It should tell you you're too young to log in or something like that, right? Whatever's the right thing. It should be robust. It should behave reliably. It should behave responsibly under every conceivable circumstance, as well as a lot of other circumstances. Then we get into the question of cost. There was a definition I ran across once of bug-free software, or what the debugging process is like. Bug-free software, from a development perspective, is you continue removing bugs until you run out of either time or money, and then it's finished. Controllable costs means saying you have got to be able to say that you can deliver a product, that you can create a software system within a certain specific maximum amount of time, under specific limitations in how much money you can spend. It cannot be an open-ended system. Now, if you're just sitting down and writing a program for yourself, sure, it can be an open-ended system. If you get it done this month, that's great. If you don't get it done until next year, maybe that's okay. But in a software system, working in a context of having a deliverable, of having a system that needs to be produced for a user, there's always a question of controlling costs. And we want to be able to... We don't want to have to be in a position of saying after it's done, well, this is how much it cost. We want to be in a position of saying before we start, this is the maximum that it can cost. We want to be able to say, we can do it cheaper if you're willing to let us make it be unreliable. Maybe that's a good choice. And as an engineer, that's the choice that you have to be able to see is going to be coming along, and tell your client or whoever it is that's commissioning you to do this right away. I can save you money. Right? This is what the penalties are. Right? I can make it be real cheap, but it's only going to run on an Apple II or something like that. Okay, that covers controllable costs and predictable schedules. Longevity has to do with the question of, well, what happens after you finish this thing and somebody says, well, I want another version of it. Now I want it to run on the Macintosh. Now I want it to turn handsprings and run on a color display and be 3D, and, you know, what do you do about that? How difficult is it to expand, to look beyond the end of your project to what comes next? Is it possible, or you have to say, can't do that. Have to start over again. Ran across that. I'm sure you're all familiar with the year 2000 problem. Air traffic control in the United States it turned out that when they started looking at the year 2000 problem, which they got around to around the year 1999 and a half, it turned out that the air traffic control systems were all written in assembly language for a computer that no longer existed, and nobody had any idea where the source code was. There was no way to fix the Y2K problem for the air traffic control in the United States. So that was very non-maintainable software. So what do you do about that? Well, if you're sensible, you move to Thailand where you don't have to fly on American Airlines. Now, this is our list. When you get into the book, he has a much longer list of qualities of good software. And some of them are just other names for what I just said. And some of them, I think, fall into the same categories, and some of them I don't agree with. So before you get started reading the book, let me tell you what I would say here. He talks about performance of software. Or I should say they talk about the performance of software as being a quality of good software. As far as I'm concerned, and I suppose this comes from my background working with real-time systems, performance, the speed that it has to work at, should be part of the specification. So it's really part of functional correctness. You know, if it has to go at a certain speed, that has to be specified, and either it does do it or it doesn't do it, and that's the end of it. So that's not really a separate thing. It's definitely not true that faster is better. Okay. There's, beyond a certain point, there's just no point in making it go faster. You know, if you're doing something where somebody is typing input on a keyboard, there's no point in making the software go any faster than a human can type. Right? There's no point in making a screen refresh any faster than the CRT can actually do it. You're just wasting your energy and probably your time. Because to make a software goes faster, it costs more. It talks about verifiability, repeatability. I'm not going to go into that a lot. Understandability. These are good things. I don't doubt that they're good things. They are very good things. But if they contribute to the cost, then they should have been in the specification. They're really things which are internal to the software. They don't impact the external world. The external world being the customer or the user. Okay. And then he gets into things like interoperability and predictability and timeliness and visibility. These are all the things that are towards the end of his chapter. And to my mind, those are not attributes of the software at all. Those are attributes of the process. And much of this course is going to be about process. But let's not confuse the two. We cannot separate software engineering or software systems from the environment that it's happening in. There isn't any such thing as ideal, pure research kind of a thing. Well, you can get a grant and do it, but that's not legitimate. In order to understand software engineering and the software engineering process, you have to relate it to the way it's fitting in a particular organization, in the particular situation that you're involved in. I could almost say that software engineering becomes a political process where you're maybe, let's say, negotiating between the physical capabilities of the computer and the requirements of the customer. That's political. It's a negotiation process. And there isn't necessarily a right answer at any given point. We want to look at three pretty distinct